When adding the imaginary number I to our number system, we get the complex numbers, a much more complete number system than just using the real numbers, which we've all used and love. Those are the numbers that include 1, 5, 18, pi, negative 23, square root of 2. All of those numbers that you're used to using, those are called the real number system, designated with the R here. Double lined R, this is the reals. And the complex numbers are in this form here. There is complex numbers have the same structure and properties that we have in our real numbers. There is one caveat, which we'll get into in a minute. Complex numbers are always written in this form: a plus bi. A and b are the numbers you're used to working with. They're called real numbers. We designate this by saying a and b are elements of the reals. That's just the math way of writing that. One exception is that when b is a radical, we put the I before the radical. So right, the square root of 2, for instance, this is a real number. And typically if we write like 3 plus root 2 I, we don't write it this way. We write it, which, you know, this right here satisfies this typical written way. We write this way as 3 plus I root 2 because just to save confusion of, in case you might be saying, well, the I is inside the radical or it's not inside of it. If we write the I in front of it, then you cannot, confuse that. It's definitely not within the radical. I use these, I myself use these little lips on the radical to show where it ends. And so it's a little bit clear when I'm writing it, I guess to me at least, but this is typically how you'll see it in a lot of mathematics, is writing the I before the radical instead of after it, the way complex numbers are normally written. Now, if you don't know, I, the imaginary number I, is defined as I squared equals -1. This is why the complex number system is much more complete, because if we say I squared equals -1, that satisfies one of the biggest issues with real numbers, namely, there is no square root of -1. This can be rewritten as I equals the square root of -1. And that means we now, in the complex number system, have square roots of negative numbers, because we can always take this out of it and it'll become a positive number underneath the radical. I'll show you what I mean by that. This video is all about just doing arithmetic with complex numbers, and we're going to be thinking about the imaginary number I as like a variable. So, for instance, if we have like 7 minus 5i, or sorry, 7 minus -5i, right? Negative and a negative cancel, become positive. This becomes 7i plus 5i. And these are like terms. They have the same variable, quote unquote, variable part, the I. So all we have to do here is add the numbers in front, and we get 12i. So just like you'd think of it as 7x plus 5x, this equals 12x. The same idea. I is just a like, think of it like a variable term, though we know exactly what its value is. Now, when you're doing, when you have a problem like this, where you have a square root of a negative number, the first thing you should always do before doing anything else is take the negative out as an I outside of the radical. So I can write this as the square root of, let me write like this first, -1 times 275, the square root of all of this. My pen's acting up. Equals the square root of -1 times the square root of 275. And this right here is I. We have I times the square root of 275. This is always your first step, is to take the negative outside the radical as an I. You don't have to do this whole long process that I just did. You can just move it on the outside as an I, because that's the correct algebraic way of doing it. Now we need to simplify the radical. We're asking for, is there a perfect square within 275? If you want to go that route, or you could say, what's the prime factorization of 275 using a factoring tree? I like to use this because it's more visual. I think it helps out more, but it takes a little bit more work if you know complete squares off the top of your head. That's a little bit faster. But 275 can be divided by 5, and that gives us 55. This can be divided by 5 again to give us 11. We have a square root here, so we're looking for groups of 2. I have a group of 2 of 5s, and 11 is not in a group of 2, which means I can take this as a 5 on the outside, giving me 5i, and the 11 stays on the inside. So this is now simplified, completely simplified, and it's made in the proper way, meaning you do not leave the negative underneath of a square root. All right, let's move on to the next problem. Here we have two complex numbers adding to each other. Well, because it's addition, we can kind of drop these parentheses. They don't really mean anything right now. So 6 minus 6i plus 3 plus 8i. 6 and 3 are like terms, negative 6i. And 8i are like terms. 6 plus 3 is 9. Negative 6i plus 8i is plus 2i, and that is completely combined. As you notice that I've written this in the form of a plus bi. That's because you always want to kind of write it into that form. That's the standard way of writing it. So try and get into that form best you can. The next one is two complex numbers multiplying each other. So we're going to FOIL this thing out. Negative 4 times 4 is negative 16. Negative 4 times I is negative 4i. 7i times 4 is 28i. And this is the interesting one. 7i times I is going to be 7i squared. Now, the 16, the negative 4i plus 28i, those are all, we've worked with those a little bit. 7i squared. Let's go back up to the definition of what I is. I squared equals negative 1. So we're going to rewrite this 7i squared as 7 times, I can say 7 times negative 1, which means we actually have negative 7. We have negative 16 minus 4i plus 28i is plus 24i. And then we have minus 7. So we can now combine negative 16 and negative 7, giving us negative 23 plus 24i. This is written as a plus bi, and that's our final answer there. It's important to note that I squared equals negative I, okay? This is a quite an interesting problem here. I equals the square root of negative I, the square root of negative 1. I squared equals negative 1. I cubed equals I squared times I, which is negative 1 times square root of negative 1, which equals negative square root of negative 1. I to the fourth equals I squared times I squared, which is negative 1 times negative 1, which is positive 1. That means I to the fifth is I to the fourth times I. I to the fourth is just 1. I is I. And we get I again. So I to the fifth equals I. And we have this, what's called cyclic behavior. I is the same thing as I to the fifth, which is going to be the same thing as I to the ninth, the same thing as I to the 13th, and so on and so forth. I squared is the same thing as I to the 6th, and so on. It's this unique number It's hard to explain what the actual value is, but it's very unique. Okay, let's move on to 3 plus 9i squared. This we can expand and FOIL. 3 times 3 is 9, 3 times 9i is 27i, 9i times 3 is 27i, and then 9i times 9i is 81i squared. I squared is -1 though, so we have positive 81 times -1 becomes negative 81. Write that out if you need to. It's important to note though that a power of I you can simplify down to, we always just write I as I. We can simplify it down to either I -1. This right here is going to be -I, and then 1. It's going to be one of those 4 values. We can always simplify it down to one of those 4 things. Okay, 9 minus 81 is -72, and 27 plus 27 is 54i. A plus bi form, that is good to go. Okay, the next problem is going to be useful for actually the one after that. Conjugate, complex numbers have conjugate pairs, and conjugates are very important in a lot of different ways. A lot of higher mathematics use conjugates as well, but it's very simple to find a conjugate. All you have to do is flip the inside sign there. So the conjugate of 4 minus 9i is 4 plus 9i. What's the conjugate of -4 plus 9i? The conjugate would be -4 minus 9i. We don't worry about this number, this sign in front. We only care about the middle number here. There's a lot of great geometric ideas with the conjugate and a lot of important properties of it. But for our purposes, we're going to use it for the next problem, which is division of complex numbers. So 20i over 3 plus I. We never write this out. It's kind of like thinking about this as like a fraction that's not been reduced. We always reduce it if possible. In this case, we can always simplify this down to the a plus bi form. The way we do that is simply multiply by the conjugate pair of the denominator. 3 plus I, the conjugate of that is 3 minus I. And then we multiply everything out. So I'm going to distribute the 20 into there, and I'm going to FOIL the bottom. 20i times 3 is 60i. 20i times -I is -20i squared. I squared is -1, so -20 times -1 is +20. 3 times 3 is 9. 3 times -I is -3i. I times +3. And I times -I is -I squared. I squared is -1, so -1 becomes +1. I'm going to write the top as 20 plus 60i, so we have the a plus bi form. And on bottom here, you see what's the important part. The conjugate pair will always cancel the I terms, meaning you only have a real number in the denominator. You never have the complex number in the denominator. And 9 plus 1 is 10. Now we can divide out the 10 from both of the terms. And we get 2 plus 6i, which is in the correct a plus bi form. That's the whole reason why we do this, to simplify it down to a plus bi form, which is much easier to work with than the division of a complex number. It's kind of a weird thing to think about, a division of a complex number, because complex, the imaginary number I doesn't quite have a good, like, understandable definition of what it means. So that's why we don't want to deal with division of a complex number. Okay, let's look at this next one. I'm going to move over a little bit. 1 plus 4i over 3 plus 3i. 1 plus 4i over 3 plus 3i. To do this, all we have to do is multiply by the conjugate of the denominator, 3 minus 3i, and FOIL it all out. A lot of foiling. Okay. 1 plus 3, or sorry, 1 times 3 is 3. 1 times negative 3i is negative 3i. 4i times 3 is plus 12i. And 4i times negative 3 is negative 12i squared. I squared is negative 1. So that makes this positive 12. 3 times 3 is 9. 3 times negative 3i is negative 9i. Positive 3i times 3 is positive 9i. And you see those cancel. 3i times negative 3i squared is negative 9i squared. I squared is negative 1. So that becomes plus 9. Right, combining like terms on top, we have 3 and 12, and then negative 3 and positive 12. Gives us 15 minus 9i. On bottom, we have 9 plus 9 is 18. Now we can break this apart and reduce. 15 and 18 can be reduced by 3, giving us 5/6. 9 and 18 can be reduced by 9, giving us 1/2. And this is the proper way of writing it. A plus bi, where a equals 5/6 and b equals negative 1/2. Okay, so make sure when you divide by a complex number, you multiply by the conjugate pair. Just like when you divide by a fraction, you multiply by the reciprocal. Kind of the same idea, but obviously not the same in the algebra. Okay, now we come to the caveat. Because I is a radical, right? If I go back up to the definition of I equals the square root of negative 1. We actually do have a little bit of issues with radicals. Whenever you're dealing with radicals, the thing you should always do first is take the negative out as an I, okay? There is some algebraic tricks you can do that if you do it correctly, you'll actually get the wrong answer. That's the only issue here. I wish it worked out the same way both ways. It should work out that way, but the number of properties we gain when using I far outweighs this one single case that we kind of lose when gaining the I. So it's just part of it. But if you follow the rule of thumb, namely, whenever you have a negative inside of a radical, take it out as an I. So take this out as an I. Take this out as an I. If that's the first thing you do, then you will never run into a problem. Okay, we have 2i root 36 plus 3i root 81. The square root of 36 is 6. Square root of 81 is 9. We have, these are multiplying here. 2 times 6 is 12i. 3 times 9 is 27i. Adding those up, we get 39i. Okay? First step, move it on the outside as an I. Gives us negative 20 plus I root 50 over 60. And we can do a couple of things here. We're going to want to break this radical or this fraction up over each individual part. I'm going to write like this instead, just to kind of keep the idea of the a plus bi form. And we need to simplify. Root 50 is 25 times 2. And the reason why I'm writing this way is because 25 is a perfect square. So we get 5 root 2. Now you can also say 50 breaks up into 5 times 10, and 10 is 5 times 2. There's a pair of 5s, the 2 stays on the inside. It's the exact same method. It's just, well, it's the exact same answer. It's just different method of doing it. Whichever way makes more sense to you, do it that way. I can divide top and bottom by 20 with a negative 20 over 60. That gives me negative 1/3 plus 5 root 2 over 60, which can be reduced by 5 on top and bottom. Gives us root 2 over 12, I think. I. And that is simplified. Okay, next problem. The first step, I'm going to take out the negative on the outside. 5i root 49 plus 7i root 64. 49 is 7 times 7, and 64 is 8 times 8. So we get 35i plus 56i. And those are indeed like terms, so we can combine them, giving us, let's see, 80, 11, so 91i. Okay. For this problem, all we have to really do is just plug in this quantity into both of these sections here. We have I plus 1 squared plus 6 over x minus I plus 1. Write that I a little bit cleaner. The top I'm going to expand so that I can FOIL it out. The bottom, I can distribute the negative into there. So FOILing the top gives me I times I is I squared, which I squared is negative 1. I times 1, 1 times I, and 1 times 1. On bottom we have 6 and negative 1, giving me 5 minus I. And we can combine like terms on top. Negative 1 and 1 cancel. We have 6 plus 2i over 5 minus I. And of course, this is a division of complex numbers. So we need to multiply by the conjugate pair, which is 5 plus I on top and bottom. Going at the top, 6 times 5, 6 times I, 2i times 5, and 2i times I is going to be positive 2i squared. I squared is negative 1, so we have negative 2. On bottom, 25 plus 5i minus 5i, and then negative I times positive I is negative I squared. Negative I squared is negative 1, negative 1 is positive 1. 28 plus 16i on top, those cancel. 26 on the bottom. Okay, 28 over 26, 16 over 26i. We can reduce each by, let's see, I think just 2. So we get 14 over 13 plus 8 over 13i. And that is in the proper form of a plus bi. So that one was a bit long here. Now, in all these problems that I just showed you, there actually wasn't any of the caveat. To get the caveat, the issue is what you really want to do here is look at a problem like this. Let's say we had negative 36 times, sorry, the square root of negative 36 times the square root of, let me use smaller numbers, 4 and negative 9. The first thing you need to do, the proper way of doing this, is to take this thing out as an I. We get I root 4 times I root 9. Root 4 is 2, so we have 2i times root 3. Root 9 is 3, so we have 3i. 2i times 3i is 6i squared. I squared is negative 1. 6 times negative 1 is negative 6. So this is the correct way. We circle it in green. The incorrect way, oops, would be to first multiply the radicals together. Which you can do. That's a property of radicals. -4 times -9 is positive 36. And the square root of 36 is 6. So you see here we have -6 in the correct way and positive 6 in the incorrect way. We have a different number, right? It's a flipped sign, which typically that's what you end up getting is the wrong sign. The right number with the wrong sign. But if this was in the middle of a long problem, and this was like in the very beginning of it, then that entire problem would be wrong because of this one single error. So make sure you never do this. The first step you always need to do is this one. Take the I out in the very first. If you do that, then the rest of the algebra works out the way you would expect, and you don't have to worry about getting this one issue wrong.